So we've seen rational functions. That's not a highlighter. We have seen rational functions already. That is a highlighter. And a rational function is any time you have one polynomial divided by another polynomial. And in the last activity that we did this morning, we saw those three different groups. What happens if the degree was bigger on the top, had a bigger polynomial on the top? What happens when the polynomials had the same degree on the top and the bottom? And what happens when the degree was bigger on the bottom? Okay? So as a result, we had some characteristics that came up. And characteristic number one that we're going to look at are our non-permissible values. Our non-permissible values result in two different things. Okay? In this example here, we have two non-permissible values. X can't be 3 and x can't be -1, because in both of those cases you would divide by 0. So your non-permissible values are always connected to when you would divide by 0. If your factors don't cancel out, like they don't in this case, nothing simplifies, they both become vertical asymptotes. However, if you have an example where, right, we still have a non-permissible value of 3, but in this example, those factors are identical and they simplify, anytime things simplify, you get a hole in your graph. To figure out the coordinates of that hole, well, after you simplify, this equation just became x plus 1. So if you want to find out, well, what are the coordinates going to be, you think of that line, x plus 1. If I plugged in 3, the y value would be 4, and so my hole is going to be at 3, 4. So you can find the coordinates of your hole if you plug in your non-permissible value into the simplified version of your equation. It's still a non-permissible value, because the original equation would cause you to divide by 0, but after simplifying it, it became just a straight line, and so you can label that non-permissible value with a hole. Oh, do we have some nice, no holes. Okay. So here's our first example. It says, predict if it has vertical asymptotes or holes. We are actually going to practice graphing these right away. So in our first one, we always start by factoring things out completely. The top is a difference of squares. Our non-permissible value, x can't equal -5. That would cause us to divide by 0. In this case, is it going to be a hole or is it going to be a vertical asymptote? It's going to be a hole because it simplifies away. The equation becomes y equals x minus 5. And so this means you're going to have a hole at, and to find the coordinates of that hole, well, the non-permissible value is at -5. If I plug that into my equation that's simplified, my y coordinate would be -5, -10. And so when I go to graph this, -5, -10, -5 here, I would have -5, -10, a hole in my graph. How do I graph y equals x minus 5 otherwise? Well, it has a slope of 1. It has a y-intercept at -5. So your graph would look like that, arrowheads on the end, with a hole in it. So you use your skills. You know how to graph lines already. The only thing different now is you've got a hole in your graph. Part B. Part B, we can factor the top. There's a common factor of 2. Leaves you with 2x plus 1 over x minus 2. And the reason we factor is to check to see if things cancel out. Our non-permissible value, x can't equal 2, because that would cause you to divide by 0. Now, is that going to be a whole or a vertical asymptote? So you can, maybe you want to abbreviate vertical asymptote. Now, when you write the equation of an asymptote, you write x equals 2. Asymptotes are equations of lines. There's an equal sign. When you write a non-permissible value, that's when you put the line through the equal sign to say that x can't equal 2. In this one, when we go to graph it, you would have an asymptote at 2, a vertical asymptote at x equals 2. What kind of graph is this one? This is one where the degrees are the same. So when the degrees are the same, we're going to have a horizontal asymptote. Our horizontal asymptote, if you look at just the x's, you have 4x over x. Our horizontal asymptote will be at y equals 4. Now that you have both of your asymptotes, you're going to need to draw your graph. How do you find out where your graph is? Well, we need some points. For example, if you plug in 0 for x to find your y-intercept, you will get 2 divided by negative 2. Can you see that that point would be at 0, negative 1? I have now found one point in this section less than x equals negative 2. So our vertical asymptote separates our graph into 2 sections. So if I want to find another point, I'm going to plug in x equals 3 or x equals 4, something to the right of my asymptote. So if I plug in 3, I'm going to get 12 plus 2, which is 14 on the top, 3 minus 2, which is 1 on the bottom. I'm going to get the point, I guess it would all be somewhere even up here, eh? Approximately 3 comma 14. And once you have a point in each section, you can now sketch your graph, okay, by showing the asymptotic behavior. So this is enough to do that in that section. And it's enough to do this in this section. Now another point that wouldn't be hard to find is our x-intercept. Our x-intercept is when y is equal to 0. And y is equal to 0 means this fraction would equal 0. The only way a fraction is equal to 0 is if the numerator is equal to 0. Can you see that that happens at negative a half? If I plug in negative a half for x, my numerator would equal 0. And so we're allowed to sketch that graph, or we're able to sketch that graph as well. Okay, question number 5 for practice. And we'll do the rest of these tomorrow. I also wanted to say that another name for whole, write this down. It's a little bit longer to write. A point of discontinuity. Discontinuity. So obviously the word whole is shorter to use, but sometimes on an exam they say, what is the point of discontinuity? And if you've never heard of that before, you go, well, what? So another word for whole. Right, so, and if you were trying to draw this all in one swipe, you'd have to lift your pencil at the hole and put it back down. So it is not continuous.